Okay, welcome back, everybody. So, last time we were here, we had just discussed moving finally to three-dimensional transformations to help us describe what's going on in the context of computer graphics. So, the first thing was translating our notion of translations from 2D to 3D. This was pretty straightforward. The reasoning was basically exactly the same as in the 2D case, so this is the matrix that gets you what you want with this same convention that you are storing these three-dimensional vectors or these points in three-dimensional space in this form. So you're storing them as XYZ1 here. This is the thing that does the translation. So the translation is encoded here, right? What is it that applying this matrix does to this vector? It does exactly this, which is translating the vector or the point XYZ to this translated thing. Okay. Now, rotating in 3D was a little bit trickier than rotating in 2D because now you can rotate about any axis rather than talking about rotating, say, about a point direction. So we still have to worry about the direction of the rotation, which we're taking as respecting the right-hand rule here. That's our standard rotation here. So that's our choice of orientation, if you like. To talk about this, we talked about rotating about the axes. So rotating about the z-axis, respecting the right-hand rule in this way, is given by this matrix. So I explained that in the last video, why this matrix does the job. Rotating about the x-axis, respecting right-hand rule here. Again, this is the matrix that gets the job done. To consider like what these other columns have to be. So we know what this column is, but the question is like where does this column go? How do the first three columns change? And this changes based on which axis is fixed by the rotation in question. So the z-axis is fixed by the rotating about the z-axis. So here's where it goes. X-axis is fixed. It's just a quick way of checking with yourself what it is that's going on here in terms of the matrix. And then lastly, our rotation about the y-axis is given by this thing. Okay. So this is what we did, and this is going to allow us to do all the rotations that we want to do. Now, you might say, well, what if I want to do a rotation that's not about one of the axes? So I'll do an example of that here in a second, but also I'll note that the examples I'll start with are when you're going to rotate about, say, an axis that is parallel to one of the axes. If you want to rotate about a completely generic axis, that's a little bit more complicated. I mentioned last time that describing these things, like if you wanted to describe these things for whatever kind of application, right, navigating spacecraft or something like that, then the thing that is probably most convenient in compact form of a description for 3D space rotations involves the quaternions, but we are specifically involving the use of matrix transformations, right? Matrix multiplication is the thing they want to get it done, so I'm not going to mention those, even though I could go down that rabbit hole and talk about those things, but I'm gonna not do that. We're gonna just focus on this stuff. So anyway, this is the setup. So a couple of quick examples using this. So for instance, quick example here. What if I want to rotate around the y-axis? So I'm going to rotate around the y-axis by 7 pi over 6 radians. And remember, the reason I'm not given a direction for the rotation here is so that I don't have to continuously give the direction. It's all of these rotations happen in the way, as I said, respecting the right-hand rule, unless otherwise noted. You could think about how you would alter these transformations if we did the rotation in the other direction. Rotating around the y-axis by 7 pi over 6 radians. What matrix would I use? This is my matrix describing rotation around the y-axis. So the matrix that I would use would be this thing which I can just directly see what this would be by plugging in 7 pi over 6 here, right? So this would be the matrix, this would be minus root 3 over 2. I'm just going to read column-wise here. 0 minus, sorry, no, that's minus, this is 1/2, 0, 0, 1, 0, 0. The next column is sine of 7 pi over 6, which is minus 1/2. 0 cosine of 7 pi over 6, which is minus root 3 over 2. 0. And then 0, 0, 0, 1. Okay. So this is the matrix that I would use to rotate points around the y-axis. And recall, if I'm rotating, say, a bunch of points or a bunch of vectors at once, I put those as columns in a matrix and apply this transformation to them so that I can do this for any number of points I wish. I can just put those points as columns in matrix. Now you might say, well, these are points in space. What do you mean columns in this matrix to make the matrix multiplication work out? Well, remember, we're storing these points in a vector with 4 entries where the last entry is 0, right? Okay. So that is the deal here. Now, what if I want to rotate about an axis that's not just one of the coordinate axes? It's not the x, y, or z axis. So here's the next example. Right? Rotate about the line. We'll say x equals 1, y equals 4, with upwards direction by pi over 4 radians. What does that look like? So we're in space. The line x equals 1, y equals 4, of course, is here's the point 1, 4, 0, if you like. The line indicated here, of course, is this one. This with upwards direction is saying that it is oriented in the same way that the positive z-axis is oriented, right? What you notice, of course, about this picture here is that this thing is parallel to the z-axis and shares the same orientation here. And so what matrix ultimately should I use in order to rotate about this line? So what is the idea? The idea, of course, is similar to what I did in the plane, right? So how did I handle this in the plane? In the plane, when I wanted to rotate about a point that wasn't the origin, I simply translated the entire plane to that point, did the rotation as if it was the origin, and then translated back. I did the opposite translation back to the initial position. So I want to do the same thing here. I want to take this space, right, as it sits here. I want to shift it so that now the origin is this point, so that this line is parallel to the z-axis, oriented the same way, lines up exactly with the z-axis here, right? I want this to line up exactly with the z-axis, and then do my rotation as if this line is the z-axis, and then translate back. Okay? Remember, when we do this, when we view this transformation as this composition of transformations here, this goes from right to left if we're thinking in terms of matrix multiplication. So the very first thing that I want to do is to shift this, if you like, I want to shift the picture. I want to shift this to the origin, right? I know that when I did this with my finger earlier, I was shifting to this point. That's well, you know, the way that I described it is fine too. So what's the first thing I do if I want to move this picture to the z-axis? The translation that I do would be the translation by the vector -1, 4, 0. Once I have applied this translation to all of the points or vectors in question, then I'm ready to do my rotation. I'm doing my rotation pi/4 radians, so that is the rotation about the z-axis, because it's parallel to the z-axis, so this is rotation about the z-axis by pi/4. Again, I know that this rotation is in the same direction because we were doing upwards direction, so it's oriented in the same way as the z-axis. And then I now translate back to my starting point by doing the opposite translation. And so this matrix product is a product of three matrices, right, that I'm not going to write down. But this matrix product, right, recall, I'm just going to flash it on the screen again. So the translation matrices, here is how we do those. And the rotation about the z-axis matrix, this is how we do that. So that when we multiply this matrix out, what we get is, I'm going to read column-wise. So this is root 2 over 2, root 2 over 2, 0, 0, minus root 2 over 2, root 2 over 2, 0, 0, 0, 0, 1, 0, and lastly, 3 root 2 over 2 plus 1, 4 minus 5 root 2 over 2, 0, and 1. So this would be the matrix that results from multiplying these three matrices. Okay. Let's do one more example like this to see what we would do. So let's say that I want to rotate around the axis given by the following line. So rotate around the line y equals 2, z equals -1, with orientation opposite to the x-axis. By 3 pi over 4. The question is, what do we do now? Well, I can draw the picture here to help, but again, you know, at some point, like drawing the picture, like you have the intuition kind of for what it is that's going on here. So if I redo this, so sorry, this is y here. Y equals 2, z equals -1. So the point is like the page. This is the YZ plane, and the line in question goes out of the page, right, or into the page. And I am taking this orientation. Here's the positive x-axis, so oriented like this. The orientation of the line I'm taking is actually going into the page, right? And so I am doing my rotation as if using the right-hand rule, I'm pointing in this direction, so that I am rotating in the opposite direction that I would be rotating if I used the positive x-axis right-hand rule respect, right? So how does this go? Well, the first thing is this point here is the point. Oh, sorry. Yeah, I mean this is the perspective here, which we're going to talk about soon, is a little strange, so you might have a hard time seeing what point this is. This is the point that I'm drawing here, 0, 2, minus 1. And so, this line is then all points, like, a generic point here is like x 2 minus 1. Okay. All right, so the first thing I do is just as before, I want the line to match up, right? Now you might complain and say, well, okay, the axis matches up, but the direction that it's pointing doesn't match up. But we'll think about that, right? Because that is not fixed with a translation, right? That will be fixed with something else. So the thing I care about for the translation is just lining up these axes. So I have the x-axis, it is parallel to this line, and I can match them up, I can line them up with a single translation, and that translation will say moves this to this point, which is just doing the translation t of 0, minus 2, 1. That moves this line to here, right? So it moves this to here. Okay. Well, now that we're there, we need to do a rotation, but we're not rotating in the way we would be rotating if we took this orientation on the x-axis as how we're doing the rotation. We're doing it in the opposite direction. Well, how can I do that? Instead of rotating in the way of the positive x-axis by 3 pi over 4 radians, I would rotate in the way of the positive x-axis by minus 3 pi over 4 radians, right? The minus sign is going to be determining the orientation here. So this would be our x of minus 3 pi over 4 radians. That would be the matrix transformation that I use. And now I shift back. And so again, I have a product of 3 matrices, and this will do it. I'm not going to multiply those out, but that's exactly what you would do. Okay, so this is giving you a little bit of a taste for what you would do when you're trying to do one of these 3D rotations about an axis that is parallel to one of the coordinate axes. Now, obviously, right, a completely generic, right, rotation may have you rotating about an axis that looks like this, right, that is not parallel to any of the coordinate axes. So what do you do in that case? Well, in that case, things are a little trickier. So note, in the case that your axis of rotation is not parallel to a coordinate axis, it's a little trickier. And it will be something you do in the exercises. Okay. Obviously, it's important to be able to do this about a completely generic axis because that's an important thing to have to deal with. If you can do it about any generic axis, then you truly can handle 3D rotations. But rather than go into that here, I'm going to relegate that to an exercise and move on to the next thing, which is, okay, we have our translations and rotations in 3D. Our original thing that we wanted to do was to investigate all the stuff in the context of computer graphics. The transformations we needed to do all this, translations and rotations, that's really what we were focused on. That's kind of what we needed. So we've got those. Okay, but now there's like one more thing to talk about, and that is how all of this translates, no pun intended, right? Not actually intended here. How all of this translates to the screen that you view these graphics on, right? So you are these computer graphics, right? You are rendering computer graphics, but they are rendered on the monitor that you are viewing these graphics on. And so that involves an operation that is neither of these things. That is not translation, that is not rotation. This is a different thing, right? What is this? This is perspective projection. You may have heard of perspective, or you may have heard of projection, right? So easy context here. You may have been tasked at some point in your life with drawing, say, like train tracks approaching a horizon, or a road approaching a horizon, right? And so when you go to do that, if you draw, like, here's your horizon, right? And you are trying to draw an image where you're looking straight. Here's your horizon, right? The sun is somewhere over here, or maybe it's not, whatever. You can just see horizon line. If you're asked to draw a straight road, right, or train tracks are a great example, because you know that the train tracks are, you know how train tracks work, and you know that if the train tracks are not straight, in a sense, right, the train is going to have problems. So train tracks approach, they are straight, they are, laid down straight away from you toward the horizon. What do they look like? If you're like, well, I know that train tracks are parallel, so here's one of the train tracks, right? Here's one of the edges of it. Here's the other one, right? It has to be like that, because I know they're parallel. So I know this is how they have to look. The problem is that, what does this look like? This looks terrible, right? This does not look like train tracks approaching a horizon. This looks like train tracks approaching like a barrier or a wall and slamming into it and then stopping, right? Like, this is not what it looks like when train tracks approach a horizon. Okay. In fact, what it actually looks like is something more like this. Where the point at the horizon, this like vanishing point thing, it looks like these things actually touch, right? And yeah, I didn't do the greatest job of drawing it here, but the point is that you could look at this and say, this isn't how train tracks are shaped. As you go far enough away, though, that is what it looks like, right? So yes, you know that the train tracks are not actually meeting, but at the horizon, the train tracks do meet. So in order to draw parallel lines that actually look how they would look if you were viewing this yourself, right, in real life, you have to draw them as if they intersect, even though you know that they don't, right? So this is an example of what is called projection, or this is like the very foundations of what we'll call projective geometry. Okay, which is kind of like a fundamental geometry. In some sense, it's kind of like the fundamental geometry, and the geometry that you're maybe more used to is built upon it with additional assumptions that make it more rigid. So this is the starting point, and in a way, projective geometry even grew out of perspective discussions. If you go back to like 1400s Europe, if you go to like 1400s England and look at the art, they didn't understand perspective. None of the artists understood perspective, so all the drawings are like 100% flat. You have a drawing of a room, it doesn't look like a drawing of a room because it's like 100% flat, and you can't, everything looks weird. It looks very strange. It's like cave paintings, or like everything is just totally flat. Everything lies in the same plane, basically. But if you look at, the Italians, the Renaissance artists in Italy were figuring out at this time perspective, and so their images looked a lot better because of this. I don't remember the exact year where this kind of spread all over Europe, so it may have been as early as like the late 1300s. I can't exactly remember, but those years are roughly right. Anyway, how does this apply to us? Well, the idea here is basically the same. we have an image in 3D. We're going to start with just a point because, of course, if you like, an image is just a collection of a bunch of points, right? So if I understand how to do this with a point, and my image is just a collection of points, then, I understand how to do this via matrix multiplication for a lot of points by just putting those points in the matrix like I've been doing this whole time. Okay. So the question, first of all, can we do projection, whatever that is, can we do projection via matrix multiplication? Because ultimately, go back to the first video, this is a couple lectures ago, go back to the first video on this stuff, our first question, our first goal that we stated was we wanted to be able to do all these operations. So translations, rotations, and projection, we wanted to be able to do that with matrix multiplication. So we've seen how to fix this so that the translations and rotations are workable, right, with matrix multiplication. Can projection be done with matrix multiplication? The answer is no, or maybe I should say not really, but there is a fix, right? I mean, there was a fix even in the case of translations and rotations that we had to do, right? So this isn't too off-putting to us immediately. But the strict answer, can it be done directly with matrix multiplication without any sort of massaging of what's going on? The answer is no. So we'll see what it is that's going on here. What is the first idea? The first idea is what we will call projection from z equals d. So perspective projection from some height along the positive z-axis. Okay. So we will call this our center of perspective. So this is our viewpoint, if you like. Okay. And where is this center of perspective? We are going to put the center of perspective at the position z equals d on the positive z-axis. And we are going to be looking at an image somewhere in space that we are going to project onto the xy plane. We're going to project a point, xyz, onto the xy plane that we're going to view as our screen, if you like, our monitor screen. Okay. So then what does this look like? All right, let's draw our picture here. So here's z, here's x, here's y. Okay. Now, here's my point at height d, so 0, 0, d. This is where my eye is, right? And my eye is looking, I'm going to draw it here. I've run out of room here, but I'm going to draw it here. Here's my eye looking straight down at this point, right? Or maybe I should say from this point. This is actually where my eye is, okay? I'm looking straight down, and the XY plane is my monitor, okay? So the first thing that I'm going to say is, let's say I have a point XYZ. It's just a completely generic point in space here. Okay, well, the thing is that I have some, so here's I'm going to draw my computer monitor screen here, right? That is the XY plane. Obviously, this extends, in all directions here. But this point does not lie on this plane. Okay, this point, we'll say, lies below it. Okay, but I want to project all of the points that are in my image that I'm trying to render, right, that I'm trying to project on the screen. I want to put them all on this screen. Now, notice that I can't simply do, like if I had a collection of points here, right? You might say, well, that's simple. Just whatever their z height is, just move it to x, y, 0, right? Every single one of these move to x, y, 0. But there's a big problem with that, right? One, this crushes a bunch of different points to that. We're always going to do some of that. So that's maybe not the biggest problem. The other thing is that it's going to look weird, right? Like it's not going to this is not going to give us the look as if we are moving, say, into the screen, right? If you know what 3D games how 3D games are rendered on a screen. You know how they look like. You know what it looks like to navigate, say, a three-dimensional map in a game, right? So you know what it has to look like, and this sort of just like shifting all these points, right, to XY0 is not going to get the job done because it's not going to look right from your perspective. You are looking at that point from this viewpoint, and that is the, I didn't draw a completely straight line here, but imagine that I did. This is the thing that gets it done. This is your view line, right? This is your line of sight, okay, with that point. And the point here is that this line of sight intersects the XY axis at some point here, which is not simply XY0. It's, I don't know what this point is, right? This point, whatever it is X0, Y0, 0. Okay. And that's what I want to find. Okay. So how do I do that? Well, in this picture that I've drawn here, you might notice, again, I haven't, this line doesn't look exactly straight. I'm sorry about that. In this picture, however, if I extend the z-axis here enough, you will see that, oh, actually, I draw in these, so if I draw in these things here, what are these angles? These are right angles, and the resulting triangles are similar. They share the apex angle here. These are right angles, and these angles, these are corresponding angles, right, formed by parallel lines, right? Remember your parallel postulate, right? Remember your fifth postulate from Euclidean geometry. These are corresponding angles, so they are congruent. These are both, they have to be right angles here, and they share the apex angles, so these are similar triangles, which means they have corresponding angles that are congruent. Okay. What that means is that I know what the ratio of corresponding side lengths has to be. The reason this is important is because the corresponding side lengths are these, right? You have this is D, and you also know what, for instance, the corresponding distances are in each of these things. So using all of this to your advantage here, and the similarity of these two triangles as I've drawn here, what do I get out of this? I can form the following corresponding ratios that have to be equal. So by similar triangles, d over the square root of x naught squared plus y naught squared has to be equal to d minus z over the square root of x squared plus y squared. Okay. Now, use polar coordinates here. If I use polar coordinates, going back to this picture, measured from the positive x-axis, both of these things, right? Think about the x-axis here, translated down. This angle is theta in both cases, right? So I'm using polar coordinates here. They have the same theta angle. Both of these points, x naught, y naught, 0, and x, y, z, have the same theta. And so I know that x is the distance to the origin, right? This is my r, square root of x squared plus y squared cosine theta, and y is similarly this, but more importantly, involving x naught here, x naught is square root of x naught squared plus y naught squared cosine theta, and y naught is square root of x naught squared plus y naught squared sine theta. Using these two and plugging them into this equation, what do I get? I get d over, I'm going to rewrite this, x naught squared plus square root of x naught squared plus y naught squared is equal to d minus z over square root of x squared plus y squared. Using these two things, what do I get? I get that this is d over, I'm solving for these things here, so this would be x naught over cosine theta, and that is equal to d minus z over, similarly here, this would be x over cosine theta. Clearing out the cosine thetas, simplifying this, what do I get? I get d over x naught is equal to d minus z over x. Which gives me x naught is equal to, and clearing denominators here, so flipping this, clearing denominators, this is x times d over d minus z. Dividing, if you like, factoring out d over d here, what I get is that x naught is equal to x over 1 minus z over d. Okay. Now, similarly, using the other two equations here in the same equation, so using these two polar coordinate relations in the same equation, I get that y naught is y over 1 minus z over d. And so, using this and what I actually wanted here, which was to find this point, I now know what that point is. So I can write it out here in terms of x and y. So again, just to remember what we're doing. We know what our view distance is, right? Our eyeball is distance d from our screen. Okay. If I have a point here in space that I'm trying to project onto the screen, my point xyz, the point on the screen is x naught, y naught, 0. I want to find this in terms of x, y, z, and d, ideally, and that's exactly what I have done. Okay. And so, this means x naught, y naught, 0 is x over 1 minus z over d, y over 1 minus z over d, 0. So, this means I seek a linear transformation f such that f takes the generic point xyz in 3D, which I am encoding in this way, as in the previous examples, and it should send it to the point x over 1 minus z over d, y over 1 minus z over d, 0, 1. Right? If such an f exists, it has to be represented by the matrix. We'll say M. We were calling it A a lot before. That is, the columns of this matrix are simply what F does to the relevant standard basis vectors, right? So here's what the columns of this matrix would look like. Okay. Now, let's do the trick that we always did to try to compute these things, right? Let's try to actually evaluate every single one of these things just using what this f would have to do based on this, right? But actually, this is pretty straightforward. It's the same trick that I always did. Okay, so going piece by piece here, right? Again, I know where f sends this. It sends it to 0, 0, 0, 1 because you just plug in 0, 0, 0, 1 here and you get 0, 0, 0, 1. Okay, so I know that one already. So I really only need to check the first three. Right? This is a typical thing that we did in these examples, right? Okay, so what about this thing? Well, using linearity, this is f of a thing I know, 1, 0, 0, 1, minus this other thing, 0, 0, 0, 1, which I also know how to find. Right, which is, this is I won't rewrite this again because we've done this enough at this point. This is how it works. What is this? F of 1, 0, 0, 1 is 1, 0, 0, 1. So this is 1, 0, 0, 1. We've already seen that f of 0, 0, 0, 1 is 0, 0, 0, 1. And so f actually fixes this vector. This is 1, 0, 0, 0. Okay. Let's do the next one. f of 0, 1, 0, 0 is f of which thing is this? This is 0, 1, 0, 1 minus 0, 0, 0, 1, which is going to give us, I'm just going to go ahead and apply f to these things. So this would be f of 0, 1, 0, 1 minus 0, 0, 0, 1, which is 0, 1, 0, 0. So f also fixes this basis vector. Okay. What about f? This is the last one I got to find. F of 0, 0, 1, 0. This is f of 0, 0, 1, 1 minus 0, 0, 0, 1. What does f do to 0, 0, 1, 1? 0, 0, 0, 0, 1, 1 gets sent to 0, 0, 0, 1. And we know that 0, 0, 0, 1 gets sent to itself. Aha. Oh. Oh, okay. So this is different. Which means, going back to what I have here, just looking, f fixes 1, 0, 0, 0. It fixes 0, 1, 0, 0. It sends 0, 0, 1, 0 to the 0 vector, and then it fixes the last standard basis vector 0, 0, 0, 1. And so if this m exists, it would have to equal, reading column-wise, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 1. That's what it would have to look like. But this doesn't work. What do I mean it doesn't work? Just check it, right? M times the vector xyz1 is not equal to x over 1 minus z over d, y over 1 minus z over d, 0, 1. These two things are not equal. So it doesn't actually do the thing that we claim that it does, right? Which is the thing we always have to check with these when we're checking what the matrix for that transformation is. So this f, this function, is not linear. This is not a linear transformation. So what do we do to fix this? How do we fix? Well, basically, the fix that we're going to do is related to our fourth component here, right? We were content to leave the fourth component being a 1 in all of these cases. It served the purpose that we needed it to serve. But now we are going to alter it slightly. So how does this fit into what we've been doing? So instead of trying to do this transformation, so we've been trying to do this. We've been trying to send that to x over 1 minus z over d, y over 1 minus z over d, 0, 1. Instead of that, let's do the following. What about, so let's try the following matrix product, which is 1, 0, I'm reading row-wise here, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, minus 1 over d, 1. Notice how this is related to the m that I found. Said, okay, if this thing is going to be linear, it has to be this. I basically took this m and I changed this, but what is this going to do? Hold on, let's see here. So what does this do? If I multiply my generic point by this thing, what do I get? I get x, y, 0, and then lastly I get 1 minus z over d. Oh. Then we divide our resulting vector by, or here, if you don't like that, we multiply our resulting vector by 1 over 1 minus z over d. And if we do that, what do I get? What does this vector become? It becomes the vector x over 1 minus z over d, y over 1 minus z over d, 0, 1, which is ultimately the original thing that we were trying to send this to. Okay. So what is our solution? Define our projection matrix P over D to be this. I'm going to read column-wise. This is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0 minus 1 over D, 0, 0, 0, 1. Then the transformation we seek is multiplying by P, then scaling the vector that results by 1 over 1 minus z over d. Or rather, dividing each entry by its fourth component. So the way of thinking about this is whatever resulting vector I get, right, I just scale the vector by 1 over its fourth slot, right, 1 over its fourth component, whatever is in its fourth component. 1 over that is what I multiply the vector by, so that the last entry becomes a 1, and the other entries become exactly what I want them to be. Okay. So we were not able to achieve our goal fully in terms of doing absolutely everything purely in terms of matrix multiplication, because this thing that we're doing is not linear. But we're almost there, right? We almost were able to do it. Basically, everything was doable with matrix multiplication except this very last thing, which was scaling a vector, which, fine, right? It's fine that we have to do it this way. At least we were actually able to do it here. So let's do a quick example here, showcasing how this would be. So here's an example. I'm not going to fully do this out because it's a pretty big multiplication, but you can just rest assured that the numbers work out nicely. So consider the 6 by 6 by 6 cube with following vertices. Now, a 6 by 6 by 6 cube here, how many vertices does it even have, right? So remember, Cube is a D6, right? A six-sided die. How many corners does it have? How many vertices? Well, it's got the top four and the bottom four, right? Or the left four and the right four, and that's it. So it has 8 total. So let's say that this has vertices, and I'm going to go ahead and put those vertices in a matrix. So the vertices are the points -3, -3, -3, which I will put in matrix form as this. All these points, of course, we're going to have a 1 in the last slot because that's how we're encoding these, right? 3 -3 -3. 3 3 -3. -3 3 -3. Okay. -3 -3 -9. 3 -3 -9. 3 3 -9. And lastly, -3 3 -9. Okay. This is my matrix. I'll call this A. So we can project all 8 points at once. Let's say D is equal to 10. That is, we're viewing this cube above the xy plane at a distance of 10. So I am 10 units up the positive z axis here. Okay, and I want to see how this goes. What would I do? I would multiply P of D, which is P of 10, times A, which I'm going to write out P of 10. I'm not going to rewrite A here because it's huge. So P of 10 here, what does that look like? This would be reading column-wise, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, minus 1/10, 0, 0, 0, 1, and then you multiply that by A. I'm not going to do that. Okay. But if I did do that, each of these columns is going to have a different result. Okay, in terms of like the last entry might be something different. So for instance, this one might be like 1.3 after I do the multiplication. The other one might be 1.9. So that's how this goes. Then, so I get a matrix and then scale each column by 1 over the column's last entry. So this will differ by column, right? This is something we have to just keep in mind. Obviously, if you were doing this one point at a time, you don't need to worry about this. You're just always scaling it by its last entry. But when you're doing a list of them, you can't scale the whole matrix by, the like the last entry of one of the columns. You have to do it individually for each column. You have to scale it, and when you do that, you will get a matrix. What does this look like if you were to actually plot this out? I'm going to draw here like an image of what this looks like on the XY plane. So the XY plane here, what does this actually look like if we project these 8 points? It looks like this. which maybe you think, doesn't look too impressive in terms of what we're doing. But if you actually connect these, you'll see what it is that's going on here, right? So this is truly a projection of the cube onto 2D, given that viewing distance, right? So the scale of this and how this looks would change a little bit depending on how close you are, right, to the XY plane, or how far away you are. But this is what you get, and there's a lot of things you could do here. In the exercises, I'm going to ask you for a lot of these, but doing this by hand is obviously very obnoxious because to make these figures look decent for what they are, you need a decent number of points, and that's something that's going to be very annoying by hand. But hey, that's why we use computational tools in this course in the exercises to talk about this stuff. And so that's the deal. You can now do all of the things that we said we were going to need to do, or said we wanted to actually talk about to make this happen. Here's the big question, maybe. Like, before we get into, I'm not going to do more examples of this because I'm going to relegate that to the exercises, because you're going to be using MATLAB or whatever computational tool you're going to be using to generate these things. What I'm going to do instead is talk just a little bit about what we might do if we were going to project from somewhere else, right? So we did a specific type of projection. So the question is, what if we were doing something else? What if we were projecting onto a different plane, right? How do we project from a different place, right? You need a few things. So need to know plane we are projecting to. Need to know which way is up for the view. So this could be specified with, a vector. You need to know like how far away the center of perspective is. But the center of perspective is going to lie on some like viewing axis, right, which is itself the perpendicular axis on which the center of perspective lies. Okay. Then what would I do once I know all of this, right? So once I know all of this, what can I do? Then find transformation that moves the plane in question to the xy plane, right? Puts the axis in question along the positive z-axis. rotates around the positive z-axis so that the up direction points in the positive y direction, we'll say, right? Is since the view of up is going to be determined by a vector in the plane itself, right? So we'll say we need to rotate around positive z-axis to put the up direction in the direction of the positive y-axis, or positive y direction. Then we see how far the center perspective is from that plane and use that for D. Then we can proceed with this as we already have. And then we get all of this stuff, right? All of the stuff that we're going to get will be in the xy plane. So then we proceed as in the previous discussions, so that now we have this set up to project in the way that we want to. Okay. Now you might say, oh my God, and now I have to shift it back. But note, we don't actually have to shift it back. The reason we don't need to move it back is because the end goal was putting this in the xy plane, right? That's the whole point. The whole point was projecting to the xy plane. So notice, like, inherently, projection is some kind of different thing, because when we were translating or rotating, we started with three-dimensional data, we'll say, and we ended with three-dimensional data. We ended with points, right? So if we were, say, translating or rotating a bunch of points, we ended with a bunch of points at the end, right? Here, while we still start and end with the same number of points, those points now all occupy a two-dimensional, they occupy a plane. So we've essentially in some way crushed the data that was in their third component for all of those things and moved that, now have we entirely crushed it? Can it be recovered? Blah blah blah. That's another question. But the point is that the end goal was moving it to the XY plane rather than it still sitting in space. So we don't need to do this moving back, because ultimately our goal was putting it in the XY plane to begin with. So once we're there, we're happy to stay. Now again, actually doing this in practice would be very obnoxious, right? Especially if you're trying to do this by hand. So this is going to be something relegated to when you have previous things worked into calculations and you can actually just use MATLAB to reproduce these things. Okay, so I think that is a good stopping point, and we have finally finished our discussion of computer graphics, so I don't think I'm going to say any more here. So I'm going to stop here, and we have one more section in like the core material of the notes, which is portfolio optimization. After that, we are going to do a discussion of linear programming and game theory, and a couple other topics that are like that I've selected at the beginning of the semester. I selected some extra stuff since I knew that we would go through all the material and have some extra time near the end of the course. So we're going to have some extra topics to consider near the end, and that's about it. So we will start with portfolio optimization in the next lecture and continue on from there. We're nearing the home stretch of the material that we're going to cover. So anyway, that is that, and I will see you all tomorrow.